Hi, everyone. Today is May 13th, and we're going to be proving trig identities, and this is going to be the first day of it. And the worksheet that we're going to do is TEI 4, okay? So before we get into this, I want to point something out. We have this is not an equation, okay? I know it looks like an equation, but what we're trying to do is show that this side and this side are actually identical. They're the same. So the only way to do that is to show that they actually are the same thing. Like you see the exact same thing on the left side and the right side. Okay, so we're trying to prove that these are equal. So what that means is any properties that we use to solve, like add the same amount to both sides, subtract the same amount from both sides, multiply both sides by the same amount, all of those things we cannot use. We cannot use, okay? Because that's assuming that this is equal, and we're trying to show that it's equal, okay? So what we do, this is just, I'm gonna go through some general strategies with you to do this, okay? One is you begin on one side. So one side of this identity you start to work on. A lot of times you want to look on something that you see like maybe a more complicated side, because something that's more complicated, you're going to be able to rewrite in other ways, okay? And then we know we're going to end when we have the expression on the other side, okay? Now, sometimes later on, we're going to be working on both sides to show that they're equal, okay? So you're just working on one side, so it's like separately, like you're going to work on the left side and you're going to get it to match the right side, okay? And then the proof, this is part 3. The proof in between consists of showing a sequence of expressions, each easily seen. Easily seen, has to be easily seen, okay? So you're making this so you're writing this for a third grader, okay? You have to show that it's easily seen to be equivalent to its preceding, the one before, expression, okay? So we want to prove this first one, and this is actually going to be a simple one, and we're going to build from like some simple ones to more complicated ones, okay? All right, but what we want to do is we want to prove that tan x plus cotangent x is equivalent, is the same as secant x cosecant x. Okay, so you look and go, can I add these? Well, we can rewrite tan x, right? So tan x can be rewritten as sine of x over cosine of x. That is equivalent to tan x, right? And so this is easily seen that tan x is replaced with sine x over cosine x. And then plus cotangent x. Well, cotangent x could be replaced with cosine x over sine x. That should be easily seen, okay? And this is equal to secant x cosecant x. Okay, so my job is to try to get these to become this, okay? So how can I do that? How can I add these, okay? So one thing you can do to add these is you could get a common denominator, right? So this fraction right here needs a sine x, okay? And I'm gonna multiply the top and the bottom by sine x, okay? So if I multiply the top by sine x, that would give me sine x times sine x, or sine squared x, over, and this denominator here would become sine x cosine x. So sine x times cosine x. That should be easily seen that all I did was multiply top and bottom by sine x over sine x, which is equivalent to 1, right? Okay. Now this one over here needs a cosine x, right? So plus, if I multiply this top by cosine x, I would get cosine squared x over sine x cosine x equals, okay, now this right side, because we're not changing it, you wouldn't have to write it. I'm going to write the secant x, cosecant x every single time, but really, I'm going to tell you, you don't have to, okay? If you don't write it, then what it means is it's the same as the line above. So you wouldn't have to write either one of these because it's equivalent to this right-hand side secant x, cosecant x, okay? That's what we're trying to show. Okay, so we switch the tan x and the cotangent x using trig identities, right? Okay, and then we looked at this and go, okay, I need to add, I could add these, and the way I could add them is to get a common denominator, which we did, right? And now what we can do is we can add these, right? So this left side becomes sine squared x plus cosine squared x all over the common denominator of sine x cosine x equals, and I'm going to continue writing this. Again, you wouldn't have to, okay? Now, we see squared trig functions, right? We should be thinking Pythagorean identity, right? Pythagorean identity, right? So we know that cosine squared theta plus sine squared theta is equal to 1. We should know that, okay? So we can replace this numerator. Now, the order's wrong, right? But that doesn't matter because the order doesn't matter when you're adding, okay? So this is equivalent to 1, okay? So we have 1 over sine of x cosine of x is equal to secant x cosecant x. And you know what? I should have said this up here. Okay, so we from here to here, what we did is we did these identities, right? I'm going to write those in red. So I'm going to try to write the identities I'm using in red off to the side. So here, tan theta is equal to sine theta over cosine theta. That's what I used to get this one. And then I used cotangent theta was equal to cosine theta over sine theta. And I used this one to rewrite this cotangent, okay? All right, so our job is to get it to look like this, okay? Now notice, this is a product, right? It's the secant x function times the cosecant x function, okay? So I could break this up because this denominator is a product, right? It's sine x times cosine x, right? Well, I could get that from multiplying two fractions, each with a numerator of 1. So I could rewrite this as, okay, 1 over sine x times 1 over cosine x is equal to secant x cosecant x. All right? Is that, and just ask yourself, is this equivalent to this one? And it would be, right? If we went backward, we'd multiply these and we'd have that, right? 1 times 1 is 1, and sine x times cosine x is sine x cosine x, okay? Now we're going to use an identity. What is 1 over sine of x? Well, 1 over sine of x is cosecant x. So this is cosecant x. That's what this one is, right? Times 1 over cosine x. Well, 1 over cosine x is secant x. Okay, and it's equal to this, right? And then, okay, so the order, does order matter when you multiply? No, it doesn't, right? So I'm going to write this secant x, cosecant x. All right, so we can change the order here, okay? And we would have secant x, cosecant x is equal to secant x, let me slide it up just a little bit, cosecant x. And we just established that they are in fact the same. This is an identity, okay? So I did, to go from here to here, right, I used this identity. I used the identity that cosecant theta is equal to 1 over sine theta. And I also use secant theta is 1 over cosine theta, right? I use those two identities to come from this line to this line. Okay, I should have written that earlier, sorry. Put a comma right here. Okay, so we established this, right? Now, why is this important? Okay, so what this really tells us that is and this is just an exercise that we need for other things, really. Okay, what this really means is that whenever you see tan x plus cotangent x, you can always replace it, if you wanted to, with secant x cosecant x. All right, so that's the beauty of these, is like you could take this and replace it with this every single time, because these are always going to be equivalent. They're always going to be equal. And that's what we did here. We established that the left side and the right side match, therefore they're equal. Okay. All right, let's go to example number 2. So some more strategies here, okay, that I want to go over. And one of them is this: begin, like I said this earlier, begin with the more complicated expression and then work towards the less complicated expression. So like in this one, okay, this left side is the more complicated expression, okay, because we have fractions and then we're adding, okay, because that gives you stuff that you can do, right? If you have fractions, okay, you might get a common denominator in order to add them, okay? All right. And then if no other move suggests itself, convert the entire expression to one involving sines and cosines. So if you don't, like if you're stuck, like you have no idea what to do, then change everything to sines and cosines, because every trig function, well, every of all these identities involve either sine or cosine. Okay. All right. Like, we're not going to do it on this one. Okay. But like secant here, the secant x could be replaced with 1 over cosine x. And this one could be replaced with 1 over cosine x. Okay. Right there in the denominator, right where that secant x is, you could replace it with 1 over cosine x. Now, I'm not going to do that because that's actually going to make it a little bit harder, because that introduces a complex fraction. Okay. All right. And there's some other stuff that we could do instead of that. Okay. So that's like a last ditch effort. You have no idea what to do, switch it to sines and cosines. Okay. So like if you see tan x, you switch it to sine x over cosine x. We actually did that on the last problem. Okay. All right. So right here, okay, we have 1 over secant x minus 1 plus 1 over secant x plus 1. Oh, and I should have said this. Number 3, okay, combine the fractions by combining them over a common denominator. We did that on the last problem, and we're going to do it on this problem too, okay? So this is going to be a little more complicated to get the common denominator though, right? So this becomes secant x minus 1, right? And this denominator is secant x plus 1. So I need to multiply this by this denominator, top and bottom, okay? And this one I need to multiply by secant x minus 1, top and bottom, okay? So this is going to be 1. I'm going to write it like this. So this is going to be 1 times secant x plus 1 over, and then in parentheses, you would have to have parentheses here, secant x minus 1 times secant x plus 1. Close the parenthesis, extend my fraction bar a little bit. Okay, so that's clear. It should be clear to you that we took this fraction and we multiply a version of 1, right? Because these match, right? Okay, now we don't want to cancel this because we're doing this to get a common denominator. So we wouldn't want to cancel these right now, okay? And then plus this one would be secant, we'd want to multiply the 1 by secant x minus 1. So this is 1 times secant x minus 1 over, okay, I know this one, we could write it first, but I'm actually going to write this one second. So it's going to be secant x minus 1. That's just so I can match up the denominators perfectly, okay? Times secant x plus 1. And this is equivalent to 2 cotangent x cosecant x, okay? Now, what I've taught you to do is, because we have common denominators, we can add the numerators and have a common denominator, right? So this is going to become 1 times secant x plus 1, okay? So it becomes secant x plus 1 plus secant x minus 1 over, okay, secant x minus 1 times secant x plus 1. And that's equal to 2 cotangent x cosecant x. We haven't even done a trig identity yet, right? Okay. Okay, so secant x plus 1 plus secant x minus 1, okay? What would this become? Okay, it'd be secant x plus a secant x, right? So that'd be 2 secant x. We'd have 2 of them. And we have a 1 and a negative 1. Those are going to cancel out. Now, I'm going to tell you something. There's something here that's telling you you're on the right track. We are on the right track. Here's what it is. We just got a 2. And you see over here we have a 2. So that's telling you that you're on the right track, okay? Now, over, okay, and this is equal to, okay? And then secant x minus 1 times secant x plus 1, okay? That's multiplying a difference of squares, right? So this is going to become secant x times secant x, which would be secant squared x, secant x times positive 1, and we're going to combine that with a negative 1 times secant x. Well, that would cancel each other out. And so then we would be left with negative 1 times positive 1. And negative 1 times positive 1 is minus 1, okay? And then this is equal to 2 cotangent x cosecant x, right? Okay. This should look familiar. Secant squared. Like every time you get squared trig functions, you should be thinking Pythagorean identity, okay? Is this a Pythagorean identity, right? So the one Pythagorean identity I want you to know is cosine squared theta plus sine squared theta is equal to 1, okay? Now, how can I get secant out of that? How can I get secant squared? Okay, that means I had to divide by cosine squared. I'd have to divide this by cosine squared x, right? If I divide this one by cosine squared x, I would get 1. If I divide this one by cosine squared x, I would get tan squared x, or tan squared theta. If I divide this one by cosine squared theta, I would get secant squared theta. Is there a way to manipulate this to get this? And there is. If I move the 1 over, I would have tan squared theta is equal to secant squared theta minus 1, right? Okay, so what does that mean? This right here, using this trig identity right here, this becomes tan squared theta, or tan squared x, okay? So this is 2 secant x over tan squared x is equal to 2 cotangent x cosecant x. Okay, now over here we have a product. So we could rewrite this as a product, okay? Okay, so we have 2, right? We have a 2 here, so 2 times, and we could multiply by secant x, and then times 1 over tan squared x is equal to 2 cotangent x cosecant x. So I'm trying to get it to match this one, right? I'm trying to get there, okay? 1 over tan squared x. Now, this is really 1 over tan x, right? 1 over tan x. And what's 1 over tan x? 1 over tan x is cotangent x, right? That's an identity, okay? All right? So if it's 1 over tan x times 1 over tan x, that's cotangent x times cotangent x. This becomes cotangent squared x, okay? So this is 2 times secant x times cotangent squared x is equal to 2 cotangent x cosecant x, right? Okay, so it's starting to appear, right? I start to get kind of excited, like stuff is starting to appear, right? You see the 2, you're starting to see the cotangent, it's starting to reveal itself, right? It's like peeling it back and you're seeing what it's going to become, right? Okay. All right. I know I'm weird. Okay. I love doing these. I think these are just a hoot. Okay. All right. That's an old word, hoot. Okay. So, all right. So right here, hopefully I made you laugh there. Okay. We need some laughter here. Okay. So cotangent x. Okay. Now I have my 2. I'm going to, and I want one of these. Now I don't want cotangent squared. Okay. So I'm going to write this as 2 times cotangent x. And I need another cotangent x, right? So times cotangent x times secant x, right? Is equal to 2 cotangent x cosecant x. Okay, and you know what? I should have said this. To go from here to here, I use the fact that 1 over tan theta is equivalent to cotangent theta. Okay, and you see, that's why I'm saying it's really important that you have these. You have these in your memory, like you have them in your working memory. I realize 5 years from now you're not going to remember this. Okay, that's okay, but you need to have it in your working memory right now, so you recognize stuff. Like if it's not in your working memory, you're not going to even think to look on the sheet to find it. Right? You got to have a working memory of it, so it's in your memory, and you go, oh, that becomes this. Okay, all right. Okay, so how do we get to here? Okay, we have a part of it, right? We have the 2 and we have the cotangent x. Okay, so somehow this is going to have to become the cosecant x, right? So what can you do, right? So what else could you do? Well, it's the step number 2. If nothing else, like there's nothing else you could do right now, okay? Other than switch things to sines and cosines, okay? So we want to keep this, right? That we want to keep the 2 times cotangent x. Okay, and then this cotangent x, okay, there's an identity, right? Cotangent x is the same as cosine x over sine x. That's our trig identity, right? Okay, and then times, and then secant x is another trig identity we could use, right? That's 1 over cosine x. And this is equal to 2 cotangent x cosecant x. And again, it's okay if you're not writing this right-hand side the whole time, okay? Okay, you'd only need to write it if you start manipulating this side, okay, to get it to match this side, okay? Now, notice something. If I move the cosine x over here, we'd have cosine x over cosine x, right? Because this is a product, right, and we're multiplying, this cosine x and this cosine x are going to cancel each other out. And we would be left with 2 cotangent x times 1 over sine x is equal to 2 cotangent x cosecant x. Well, they're not the same yet, right? They're not the same yet, but we're darn close, right? Okay. So what did we do to go from here to here? We use the fact that cosine or cotangent theta is equal to cosine theta over sine theta. We also use the fact that secant theta is equivalent to 1 over cosine theta, right? We use these two identities to go from these two to these two. Okay, now 1 over sine x, right? What is 1 over sine x? Well, that is cosecant x, and we have it, okay? So now we've established that 2 cotangent x cosecant x is equal to 2 cotangent x cosecant x. Okay, and the trig identity I use to go from here to here is that cosecant theta is equal to 1 over sine of angle theta. Okay, and that's always true. Okay, notice something. I want to say this again. Okay, you might be tired of me saying the same thing over and over again. Okay, this is not an equation. We're trying to prove that these two things are equal. Okay, so we cannot move stuff from one side to the other. We can't add, we can't, like in this case, we can't divide both sides by 2 to get rid of the 2. You can't do that because that's assuming that it's equal, and we're trying to show that they're in fact equal, okay? It's really important. You can't add the same amount, you can't multiply the same amount, you can't divide by the same amount, you can't move stuff from one side to the other, okay? Because that, you can do that, all right, when we know it's an equation and we know it's equal and we're trying to solve. Those are properties of equality that we're using. And the problem is we don't know if this is equal or not. We don't know if there's equality here or not. We're trying to show that they're equal, okay? All right, enough said on that, okay? All right, so what does all this mean, okay? All right, so back up here, okay? Whenever we saw this, what this means is whenever we saw this, now this is not something I'm expecting to memorize, okay? These are just exercises, okay? Whenever we see this, we could replace it with this simpler thing every single time, okay? And that's what we're trying to get to, is we're trying to get to things that are complex looking, and it's going to make them simpler, okay? And we're getting there, we're building, okay? All right, let's go to example 3. Okay, so the next strategy is using the algebraic identity a plus b times a minus b is equal to a squared minus b squared, okay? If we do that, it sets up a lot of times a Pythagorean identity, okay? And always be mindful of like where we want to go, right? What are we trying to get to, okay? And you want to jump on manipulations that would get you there, get you closer to it, to getting it to be what you want, okay? So you look at this one, okay, and you want to prove the identity cosine beta. By the way, this is a Greek letter B, it's beta, okay? And then, so cosine beta over 1 minus sine beta, right? And then 1 plus sine beta over cosine beta, okay? So you look at this and really there's not one side that's more complicated than the other, honestly, okay? I'm gonna work on I just tend to work on the left-hand side when there's no choice right here, really. Okay, so there's no choice of one side or the other, okay? I'm looking at this left side. What I want to get is a 1 plus sine beta on the top, right? Okay. So what are some things you can do? I can't move stuff. I can't cross multiply. I can't do any of that with this, okay? But what I could do, okay, what I could do is multiply by a version of 1, okay? If I multiply by a version of 1, okay, I would want to pick it so that 1 plus sine beta is it, right? I would get 1 plus sine beta on top. So that's what I mean by be mindful and then favor manipulations that bring you closer to your goal. So if I multiply by 1 plus sine beta over 1 plus sine beta, okay, that would get me a 1 plus sine beta on top. Okay, we'd have extra stuff, but maybe we can get rid of it. Okay. Okay, so I'm going to work on this left-hand side. So I have cosine of beta, and I'm going to multiply the top and bottom, and I'm going to multiply the top and bottom by 1 plus sine beta all over 1 minus sine of beta times 1 plus sine beta, right? 1 plus sine beta over 1 plus sine beta, that's 1, right? I'm multiplying this fraction by 1. So is that an easy step to see? It should be, okay? All right. Okay, so now this becomes 1 plus sine beta over cosine beta. That's what we're trying to establish, right? Okay, this is actually probably gonna be the easiest one, okay, in all honesty, okay? I think the start is probably hard, but the manipulation from there is not that hard, okay? All right, so right now there's nothing we can do on this one, okay? And we can't even switch things to sines and cosines because they already are, okay? So what we have here what else could we do? So like that's the question, like that should be going through your mind, like what else could we do? What else could I do? Well, how about multiplying this out? Now notice this is a difference of squares, right? This is the factoring of difference of squares. What if I multiplied it out, right? And that's what we're talking about here. What we have is something that looks like this, right? We have 1 in the A spot, right? And we have sine beta in the B spot right here, right? And so when we multiply them, we're going to get 1 times 1, all right? And we're going to get 1 times positive sine beta. That'd be just sine beta, positive sine beta. And we'd multiply negative sine beta times 1. That'd be negative sine beta. Well, we have a positive sine beta and a negative sine beta. Those are going to cancel, right? And we have a negative times a positive, so that's going to be negative, and this would be sine beta squared, okay? So I know that's a lot to say without writing anything. Okay, so cosine beta times 1 plus sine of beta over, okay, if I multiply this, I would get 1, right? Because 1 times 1 is 1. And then 1 times sine beta, positive sine beta, negative sine beta times 1, negative sine beta. Those are going to cancel. And we're left with negative sine beta times positive sine beta. That'd be minus sine squared beta, right? And this is equal to 1 plus sine beta over cosine beta. All right. Do you see where we're going to go with this? 1 minus sine squared beta, 1 minus sine squared beta. Okay, squared trig identity, right? Squared trig function. We should be thinking Pythagorean identity, right? We know that cosine squared theta plus sine squared theta is always going to equal 1, right? Okay, can I move stuff around to get this? Yeah, I can move the sine squared theta over to the other side. So I would have cosine squared theta is equal to 1 minus sine squared theta. Well, instead of theta, we just have beta over here, right? So what does this denominator become? It becomes cosine squared beta, okay? So cosine of beta times 1 plus sine beta over cosine squared beta is equal to 1 plus sine beta over cosine beta. Okay, so you should know, like, hey, I'm starting to get in the right way. I'm starting to get there, right? It's starting to peel away and it's starting to reveal itself, right? Why? Why am I saying that? Because we need a cosine beta in the denominator, right? Guess what? We just got it, right? Now, what does this square mean? This square means cosine beta times cosine beta. So one of those cosine betas is going to cancel with this cosine beta on top, right? Because that makes a 1, right? Okay, so what are we left with? Well, this cosine beta, okay, will cancel with one of these, right? And so we'd be left with 1 plus sine of beta over cosine of beta is equal to 1 plus sine beta over cosine beta. Okay, and we've established that they are the same thing. These two are equivalent. Okay, now some of you might have wanted to work on the right hand side, right? Okay, so if you look on the right hand side, okay, one of the things you could have done, there's and let me tell you this, there is more than one way to do these. Okay, so like looking at this, okay, um, let's say we wanted to manipulate the top, right? Okay, we could, if you look at this right hand side and you look at the left, like I want to get to the left hand side, right? I could multiply top and bottom by cosine beta, right? Okay, and then I'd have cosine beta, but then on the bottom I'd have cosine squared beta, and then with the denominator here being cosine squared beta, I could manipulate that and rewrite it using the Pythagorean identity, okay? And then do some canceling, and I would make this right side match the left side. Okay, so if you did it that way, you're absolutely right. There's nothing wrong with that. You just have to show through a sequence of easily seen steps that the left side and the right side are indeed the same thing using fundamental identities, okay, and algebra manipulation. You can show that one side becomes the other side without, again, I'm going to say this, without moving stuff from one side to the other. You cannot do that. I'm going to say that 100 times. I see it all the time teaching this class. You cannot move stuff from one side to the other because that's assuming equality, and we're trying to show that it's equal. Okay, when I say equality, that means equals. Okay, all right. Okay, guys, that's example 3. I think that's the last example for today. I won't be like yesterday and mess up and think I have another example. Okay, let me get the assignment sheet and we'll finish this up. Okay, guys, so what I want to do is today is I want you to do worksheet TEI 4. Okay, this is the 13th. Okay, and you guys, I'm going to say this several times. I'm okay if you're a day or two late. Okay, a lot of you guys are so sweet. Okay, you guys are emailing me and saying, Mr. Mitchell, I'm so sorry I can't get it in on time. Don't worry about it. Okay, do not worry about it. Okay, we're in crazy times. Don't worry about it. Okay, I'm just happy you're doing assignments. Okay, now I do want to say this. We do need to do all these assignments. Okay, we need all of this stuff for calculus. Okay, so if your intent is to take calculus, you need to get these done. Okay, and this is going to sound harsh, and I want to say this instead of sending a message. Okay, you guys, I'm gonna have to take you off the calculus list if you're not doing these assignments. Okay, and I hate saying that. Okay, but there's no way you're going to be able to handle calculus if you don't work through this. We're going to have a tough enough time without you not doing any of these assignments. Okay, so we got to complete these. Okay, you don't have to be great at it. Okay, you don't, like, that's the beauty of this, is like I am not testing you right now, right? There's no way for me to assess you, so just do them and try to figure them out on your own. And when we come back to school, okay, in the fall, hopefully we come back, okay, I will do, there's going to be some gaps that we still have, okay, and I totally understand that, but I can't fill all of these gaps. Okay, all right, there's going to be things that come up, and I'm already planning on stuff to review with you guys. Okay, so just know that. All right, those of you who are taking calculus, I mean, if you're not going to take calculus, you don't need this. Okay, to be honest with you, you don't. Okay, it's not like, oh, you can't live without this. Yes, you can. All right, okay, but you do need this if you're going to take calculus, because there's a lot of these trig identities that we use, that we swap out to make things easier. Okay, all right, to make things easier. And if we don't know them, you're not going to make things easier for yourself. Okay, you're just going to sit there and stare at a problem. Okay, all right, guys, so just do worksheet TI 4. I've talked long enough. All right, I just think the world of all of you guys. I can't believe how many of you guys are doing assignments and turning them in, and I'm just so pleased with you guys. Okay, I am bragging to everybody about my honors math 3 classes. Okay. You guys are kicking butt. Okay. Hang in there, guys. Have a great day. I'll see you tomorrow.